Dr. Ghosh.
Yeah.
Maybe.
So with your kind permission, sir, should we start then?
Yes, yes, yeah.
Yeah. Okay.
I think a lot of participants are joining, so it's okay. You can start it.
Yeah, sure, sir. So I am Dr. Taposh Ghosh, Assistant Professor in the Department of Applied Sciences, MAKAUT, West Bengal. I will be moderating this session of this webinar. And on behalf of the organizing committee of this webinar, a very warm welcome to all the esteemed panelists and participants to this webinar. I'm very thankful to all the attendees for their precious time to join the webinar on transforming science education and research through computation, intensive tools of learning. Today, there is barely a scientific fraternity where computation didn't play a pivotal role in their growth, be it industrial process, application in medicine, or in software industries. Our Honorable Vice Chancellor, sir, has foreseen that the field of education will not be an exception. So he has inspired and convinced us and encouraged us so very many ways to emphasize on computational applications while designing the courses for our in-house UG and PG programs like MSc in Applied Chemistry or be it in MTech in Material Science and Technology, to name few among many. I truly believe that all of us will be highly benefited out of this webinar today, and there will be a lot of new knowledge to take away at the end of the webinar. So before we proceed to our next sessions, I would take the opportunity to introduce today's panel members. And today we have with us our Honorable Vice Chancellor, Sir, Professor Dr. Shoykot Moitra, Professor Dr. Shukhendu Samazdar, Director of School of Natural and Applied Sciences, Dr. Atrey Bishwas, Head of the Department of Applied Sciences, MAKAUT, West Bengal, Dr. Arijit Bagh, Associate Professor, Department of Applied Sciences, and of course, none other than our distinguished keynote speaker, Professor Dr. Saurabh Pal sir, and Director of Indian Institute of Science Education and Research, Kolkata, and also former Director of CSIR National Chemical Laboratory, Pune. So with this brief introduction of the panel members, may I now request our Honorable Vice Chancellor, sir, to inaugurate the session and deliver his inaugural speech. Sir. Hello. Hello.
Hello.
VC sir, can you hear us?
Are you talking to me?
No, sir. Talking to Professor. Sir, can you hear us?
Yes, I can hear. Internet connectivity.
Yes. If you would like, kindly inaugurate the session and
yeah,
please.
I think sir might have some internet issues then, I guess.
Looks like it.
Yeah.
Vijay sir, are you able to hear us? Hello? Hello?
Yes, sir.
There is some internet connectivity.
Technical glitches.
Sir will log in soon.
Yes.
I'm trying to establish connection from different routes.
Okay, sir.
The
Okay, sir.
voice is coming, sir.
Yeah, yeah.
Yes.
We are able to see you and hear you, sir.
Okay, okay.
Such
But
difficult
internet
spice.
morning internet is Professor Samasda, who is going to start?
I think if you would give the inaugurate it, and please, if it is okay at your end, otherwise.
I think it is okay. I can start my presentation sometime.
I think without wasting time, because I am facing some problem with internet connectivity here.
Okay.
Yeah, let us start.
So
So-
I think Professor Saurabh Pal can start his presentation.
Yeah.
Professor Saurabh Pal, kindly start your presentation, and afterwards, if this situation becomes normal, then I can continue.
Sure, sir. Sure, sir. Whatever you say.
So can I share the screen? Hello, can you
Yeah.
hear me?
Yeah, sir. We can hear you.
Can I share the screen then? I'll start.
Yes, please.
Yeah. Sure, sir. Sure. Please, sir.
Before that, if you don't mind, Dr. Bagh, if you would introduce Professor.
Yeah, sir. So, allow us, sir, please, kindly to introduce you.
Yeah, let's do it fast. Yeah.
Okay, okay. Thank you, sir. So, may I now request Dr. Bagh to kindly introduce our keynote speaker, Professor Dr. Saurabh Pal, sir. Please, Dr. Bagh.
Yeah, thank you, Dr. Ghosh. Please allow me to share my screen so that. Yeah. So it is a great honor to me to have this opportunity to introduce such an eminent personality like Saurabh Pal. So Saurabh Pal, Professor Saurabh Pal is recognized as one of the uh, six most successful honorable fellows, humble fellows in India out of 1,365 fellows. Very recently, this record has been produced, and he is also recognized as has been nominated to be on the first executive board on of newly constituted Federation of Commonwealth Chemical Science. Professor Saurabh Pal was the former director of the National Chemical Laboratory from December 2010 to May 2015, and presently he is the director of IITs Kolkata. He is acting as director of IITs Kolkata from October 2017 till date. He got the Shanti Swarup Bharnakar Award in 2000 for chemical science and received from Honorable Prime Minister of India, late Sri Atal Bihari Vajpayee. He is also the recipient of Shastra C.N.R. Rao Award for chemical science and chemical material science in 2014. He started his journey as a integrated MS student of IIT Kanpur and got his degree in 1977, and then he joined Indian Association for the Cultivation of Science for his PhD work under the guidance of Professor Devashish Mukherjee and awarded in 1985. Then he went to the University of Florida for his postdoctoral work, and he worked with renowned Professor Rod J. Bartlett. Here are a few captures from the old days, and then returning back from Florida, he joined NCL Pune as a scientist and started his own career. This is a picture from those days, and this is the picture of Professor Ramkinder Roy, one of the first batch student of Professor Pal, who actually not able to pursue his work with Kapil cluster theory, and then Dr. Pal started working on a different area along with the Kapil cluster theories. And in this way, he actually has a wide range of research interests. Some of is mentioned here, like the development of molecular electronic properties, the investigation of hearts of acid-base relation, the molecular scattering. They also use density functional theory methods for nanoclusters, catalysis, and hydrogen storage materials. He has guided more than 32 PhD scholars, and he has a lot of publications, more than 270. There are a few photographs of this group taken in different times. This is the photograph of 2014 TCS at NCL. He has honored and different prizes, including Shantishwar Bhatnagar Prize, Yeshivas National Fellowship, and he is also fellow of different academic of India and abroad, including Indian National Science Academy, National Fellow of the National Science Academy of India, and so on. They have delivered a lot of invited talks around the globe. Few are mentioned here, and he is also the member of different editorial boards of journals and societies. Few of them are mentioned here, like International Journal of Molecular Science, Current Physical Chemistry, Journal of Chemical Science, and so on. His contribution to Indian science not included the research work, but also his diverse magnitude of work. Particularly, he started industry academic collaboration in NCL, and also he started entrepreneurship development in IISER Kolkata. He is also an active participant for establishment of IISERs. With this, I like to invite Professor Saurabh Pal to deliver his keynote speech. Thank you. Sir, please.
Can I start?
Yeah.
Yeah,
Yeah, sure, sir. Please.
please, sir.
Is the screen seen?
Yes, sir.
Yes,
Are
sir.
you able to?
Yes, sir. Your screen is visible, sir.
Okay, thank you. Thank you, Professor Shaikat Mitra and Dr. Tapas Ghosh, Atre Biswas, and all others for inviting me, Arijit Bab for giving a kind introduction. Am I audible?
Yes, sir.
So, yeah, I was thinking of a topic for this webinar when actually MAKAUT itself suggested the topic. So the title that you are seeing, I must thank MAKAUT for giving the title. So I was more or less kind of fixed, because I think I gave a similar lecture in a CSIR summer research training program. So I was thinking actually slightly different lecture, but eventually the title is very similar, what MAKAUT suggested: Transforming Science, Education and Research Through Computation, Intensive Tools of Learning. Actually, let me say that although this title suggests that the computation used to integrate education and research, most of the lecture would be computation for education, or computer tools for education, and computer tools for research. It's very interesting that today computer has come in the focus because of the COVID virus, because of the fact that that is one way that we can still communicate, and the science of computation, science which uses computation, can continue uninterrupted. So I think that is where computation has come as a very important tool in today's world. So that is the reason I think people are discussing this. But computation, of course, for research existed long back. Computer tools for education also existed before the COVID came. But I think their importance is now been highlighted. In fact, various universities, institutes are giving lecture on online teaching. In fact, I must say that in our ISER today itself, Professor Soumitra Banerjee gave a nice talk, who is the Dean Academics, on how to do online teaching, and several computation tools were discussed. So I think it is nothing new. But today, somehow, computer has been integrating education and research, and so that would be the message. So there will be two parts to my talk: one for education, another for research. And somehow we can say that they're connecting, but the tools that are used are obviously quite different. The tools that will be used for education would be quite different from the tools that will be used for research, except the fact that they're of course commonly connected to the computer tools. I am of course currently in the IISER Kolkata, and as was mentioned, I was also also at the National Chemical Laboratory, Pune, and then I was at IIT Bombay for a short period of time. So let me just see that. I hope it is on a slideshow mode. Okay, so I made it on a slideshow mode. So I'm very thankful.
Sir, so it is static, sir. Yes, sir.
It is static?
Yes, sir. Yes, it is. Yes.
It's moving, right?
Yes, sir. Yes.
Yeah. So, yeah, please let me know if there is any problem.
Well, it's perfect now. It's perfect, sir. Please proceed.
I just went to the full screen mode. So I love to see these three cities where I have lived my life. Pune on the right corner, the bottom, Mumbai on the left of the bottom, and this is where I am now currently staying. So it's a very interesting part, and each city has its own ethos. Each city has helped me to grow. So I'm also thankful. In fact, all of us should be thankful to the location, thankful to the places where we grow up, because there's a culture which you imbibe. I must say a few words about ISERs, because the topic that we are talking today is very important to ISER, because we are talking of integration of education and research. And I must say that this is the whole idea with which ISERs are formed. And I have been involved with ISERs from its beginning, actually. Although I came to ISER formally today, I have been adjunct professor of ISER Pune, and I was also in the implementation committee of ISERs, which took place in Pune in 2006 February. There is a syllabus committee which I had conducted. So I'm aware that the ISER has been from the beginning given a thrust to integrating education and research, integrating also research and innovation in various forms, not only in education, but also in research. So as you see that ISER Pune and Kolkata came in 2006, ISER Mohali came in 2007, Thiruvananthapuram in 2008, Thiruvananthapuram in 2008, as well as Bhopal, and then Tirupati and Berhampur came in 15 and 16. So these are the 7 ISERs, and they have a common goal, although each ISER's curriculum to an extent is different. So each ISER is autonomous. I must also say that each ISER has its own academic senate, which approves the degrees. Each ISER has its own board of governors, which takes decision, but there is a commonality among the ISERs, and I think that is very important. So to impart science education, basic science education, to impart education with research, And that is the reason our flagship program, BSMS, has a final year research component, which is very, very important. We also have integrated PhD and a normal PhD programs in various departments. Departments continue to grow. New departments continue to establish. As of now, we are giving degrees in 5 departments: biology, chemistry, art science, physics, mathematics and physics. But we have several interdisciplinary centers for research. Some of them, like space science, also gives a degree. So basically, I think we are evolving. We now have humanities department. We also have a computer science department, although the degrees won't be given, but they will be helping conduct our courses for the other department degrees. So we continue to grow, and I'm sure one day ICER, character of ICER also will change a little bit depending on the needs of the society. So this is, of course, the campus, and I'm very happy to say that MAKAUT is one of the closest institutes from ICER Kolkata, certainly the closest university at this stage. And we are very happy. I'm very happy to be invited by MAKAUT. And I'm sure many of the MAKAUT faculties have already been in the campus. So this is a snapshot of the campus. The campus first phase buildings are almost over, actually. And we hope to get more money to build the second stage. We also have, apart from normal education, ICER research, we also have innovation complex, which we are just setting up in the RISE ICER. And I hope many of the research will be translated to the RISE ICER. I'll come to that a little bit later. We are spread in 201 acres of campus with a lake, and we have very consistent NIRF ranking. The latest NIRF ranking of ICER Kolkata is 29. That's the overall ranking. Of course, we don't have a separate science ranking, unlike engineering and others. So our overall ranking is 29, which is sufficiently good, but we think we can do better. And I think we can even come within the top 20 in immediate future. Let me just talk about science education itself, where it is today, what is the hierarchy of science education, and how do you integrate research with education? I think this is a very fond theme of ICERs. And I must, of course, say about COVID-19, because that has thrown a lot of challenges. And certainly there are more opportunities, at least for science education, but certainly a lot of challenges for research. And one of the major opportunities come because of the online teaching or online learning. And I think, as I said, this is not a detailed talk on online teaching alone, but a few things, few points of what I will highlight. Of course, you all know why we need to learn science, because that provides a basic expertise of physics, chemistry, mathematics, biology, geology, etc. And that gives us the impetus to do research, and research, which is basically interdisciplinary. It's very important today to understand. We have opportunities for academic research, teaching, industrial research, and many alternate science careers like communication, science communication. I think it's a very, very important area today, journalism, and so on. But very importantly, and that's the reason I took up science, and I must write this, is the freedom that the science gives and the fulfillment of mind. The mind becomes full, and I think that's a very, very important reason that I took up science. I didn't really realize what science is going to give me at a young age, but when I went to IIT at the age of 17 in IIT Kanpur as an integrated student, I could have taken engineering actually, because I went through the IIT joint entrance and I would have got any engineering department I wanted. But I decided to take up science because I felt that science has a romance. Science helps me to think freely and fulfills the mind. I think we didn't know all that I know today about what are the opportunities that the science provides. So the opportunities to give you very briefly are research and teaching in academic institutions. I must say that although we call academic institutions, they have very good research facilities, IITs, ICERs, NITs, universities, private, state, central, similarly all colleges, private, central, state. Of course, research laboratories like CSIR, and I have been in CSIR laboratory of National Chemical Lab, IISc Bangalore, Tata Institute of Fundamental Research, Indian Association for the Cultivation of Science, many others. I mean, I must say that Hava Atomic Research Center, and just several DST, DBT labs, and so on. It's impossible to even write them down. We have similarly even academic institutions. There are institutions like Homi Bhabha National Institute, which are coming up. So many other possibilities are there. Then there is a box which I call mission-driven research, which are basically, like I said, BRC, atomic energy, space, defense. There are several DRDO labs, ISRO, and so on. So that's a great opportunity. Of course, R&D. And I think industry R&D is going to become more and more important, particularly pharma. We know how pharma is important today in COVID research. We are all hearing what Glenmark is doing, what Lupin is doing, what Cipla is doing. And I think it's very, very important to get into a very good industry, do R&D in industry. What I just now said, that we have innovation complex, which is going to encourage entrepreneurship. Entrepreneurship, encourage startup companies based on what I now call deep innovation. So these are not jugaad. I hope you have all heard jugaad, which is basically a low cost, low technology innovations. So what we require is not just jugaad, because India has been very good in jugaad. That is called the frugal innovation. I think many of you might have read, India is a center of frugal innovation. But what we require today is what I call deep innovation. So that's the high-tech, high science-driven innovation. And I think that is where we are lucky. So there are lots of opportunities for research, and of course, there are opportunities for international collaboration. The important thing to realize is the fundamental science cannot be predicted. And I think that is a very important part. Most people think that fundamental science is a curiosity-driven science, research. And that great example is Isaac Newton. And I always wonder whether anybody did not see the apple is falling downwards, or did they see and they could not find what is the reason. But Newton saw, found the reason. That's of course, a story, but it's a very nice story to show how curiosity drives the science. Of course, science has also come out of accident, and it's very, very important to know. There are several examples in chemistry and biology, microorganism in biology. For example, a lens grinder found it. A Dutch lens grinder who was not actually interested in looking at microbiology. Of course, urea synthesis in chemistry is a great example which came out of accident. Then there are examples which are necessity-driven. Archimedes, the great Archimedes, who found out his Archimedes principle, was actually driven by the necessity, because his king actually gave a challenge to find out if his goldsmith is mixing silver in the gold. And those days, if he could not have found, he might have been even killed. So in a way, it was a necessity-driven. I also can add dreams, and I will give examples that certain innovations have come out of dream. The great example is again a structure of benzene, when Fred Kekulé actually dreamed that the snake is seizing its own tail, and that's how we got the ring structure of benzene. So I think there are several ways that science, fundamental science grows. In fact, many people come and ask, how do you do research? How do you do original research? I don't think there is any textbook that you can actually say that this is how we should do research. And that's what I'm trying to say. What is important while we are doing research and getting fundamental understanding, we must start to use them. So this is a very, very famous quadrant that I want to show. And this is the low quadrant, where use as well as the fundamental understanding is low. This is the applied research is very high. It's the Edison quadrant. The science is not very high. This is called the Bohr quadrant. At least when Bohr discovered the atomic theory, or his first atomic theory, people didn't realize the importance. So it was called pure fundamental research. And then there is a research which is called the use-inspired basic research, which is Pasteur quadrant, Louis Pasteur, which is basically high science combined with high use. And I think this is where we must go. We must go from here to here. The problem is when the students come, they're here. They have neither the great understanding of science, nor they know how to apply. How do you bring students from here to here? Usually, we end up bringing them in the Edison quadrant. Not that they're going to become Edison, but I just mean that we end up bringing in this quadrant. or we end up bringing them in bore quadrant, where they're great scientists, lots of understanding, but rarely are we able to bring them in this quadrant. And that is the problem of India. Either they have a good technologies, but low science, good scientists, no idea of technology. So one has to understand. Very often when we come here, the ego, and I must say this was actually written by C.P. Snow, the ego of the basic scientist prevents them to go to the pasture quadrant. And this is a very sad thing to say this. So how do you bring students this way, or is there a diagonal way of bringing them? I think that is what the educators have to think, and it's not very easy. Obviously, because we have not been able to bring the science to that forum, we have missed out on the Nobel Prize, because Nobel Prize has a very important understanding that the science should be also translatable to the society. Of course, I have just focused on the 4 Nobel laureates who are Indian and Indian origins, so C.V. Raman, Hargobind Khurana, Chandrasekhar, Venki Ramakrishnan. Of course, C.V. Raman, I must especially say, because he walked within it from India to get the Nobel Prize. But the point is, where is the next one coming? I mean, many people worry about that. And I think this is where we have to catch up. We normally would say that we have to catch up with the Western world, but let's not forget that the ancient Indian science was quite developed. But the problem is that we should not also get fixed there. We must think beyond, and we must think rationally. But let's not forget that there are inventions in Indian science which are great, like zero number theory, for example, originated from India. Entire area of Ayurveda came from India, geometry, algebra, and I've even seen long back computer algorithms written to solve differential equations. It's amazing, actually, that such a thing happened in India much before the algorithms came. You know, that was written. In fact, I have very nice text of history where even algorithms were written in India. But somehow we lost it, and many of the new things we need to catch up today. When we talk of science, there is a hierarchy, perceived hierarchy, but I have to say that the hierarchy is breaking down. So I take 3 disciplines which are very popular: chemistry, physics, and biology. I'm not going to talk about geology or mathematics. Mathematics will come, of course, as a tool, but I think it's a hierarchy that is somehow perceived. When you look at chemistry, and I must say I'm a little bit biased, because I will talk a little bit more about chemistry, there is no instinctive knowledge to start with. So chemistry looks very complex to understand. What I mean by instinctive knowledge is that when a child grows up, it doesn't see molecule, doesn't see a reaction, how the reaction takes place, only sees the end product. But when you look at physics, it is the world, They look at cricket ball, they see apple falling. It is something that they grow up with. Biology, of course, is very complex, but you can still feel it. You look at a plant, you look at an animal, and you feel biology from the early childhood, but you don't see chemistry. There is no instinctive knowledge. So chemistry is usually imparted by a transfer of knowledge. Somehow somebody has understood who also didn't understand in the childhood, and later this transfer takes place. But there is a considerable evidence that both learners failing to make sense of teaching and students developing certain alternative conception of the material presented to them. And they have a wrong perception of chemistry. That's why chemistry is very difficult to teach. And many people as a young children in school, they either like physics or biology. Very good students. And I think this is, again, you may think it's a biased comment, but this is what I've seen, because physics and biology are something that you feel. However, chemistry is a central science, and that is very, very important. Later on, people realize that even physicists who are working on materials realize that without chemistry, there is no materials. So chemistry is, of course, very, very important. But it is very hard to believe that most physical chemists are working within the same paradigm as most organic chemists. The paradigm of organic chemists are somehow different than physical chemists. Of course, you can talk similar about other subjects, but physics somehow have some commonality, whether you're doing classical mechanics, electrodynamics, quantum mechanics. Biology is a broad discipline, but there are certain commonalities. But the chemistry, you think that the physical chemists work more in the paradigm of physicists, organic chemistry or synthetic chemist paradigm is different. And that has been the problem, but chemistry is a single discipline. So the hierarchy of science really builds upon each other. So for example, it is understood, and this is again a perception, you may not agree, that physics is built on mathematics. Chemistry, whichever way you argue, it is still built on physics. There are certain physics tools, physics theories, which actually make chemistry, whether it's a synthesis, there is a thermodynamics, there is a kinetics, and those are basically like physics. Biology builds on chemistry. Again, this may be a very debatable point. Sorry, biology depends on chemistry, and the psychology similarly builds on biology. But again, this is a very one way of looking into it. There are no equivalent, there are not necessarily equivalent. So maths is a tool which is used heavily in physics, but it can be used in biology. As all of you know, data science is becoming very important in biology. It is of course used in chemistry, like quantum chemistry and so on. There are large parts of biology that make direct or indirect applications of chemistry. So there is biology which has nothing to do with chemistry. Similarly, physics, chemistry is not reliant on physics, and so on. Psychology builds heavily on biology and chemistry, but there are parts of psychology which can be seen as social sciences, which has nothing to do with biology. So I think what I just showed as a hierarchy is a very rough hierarchy. It's a perception. It is not correct. When we talk about chemistry, language becomes very important. And this is a language, the atom. So when you do chemical experiments, they are different from chemical language. So one has to understand not just the experiment, but also the different levels of chemical language. And that actually gives you the history of chemistry. If you see, in the chemical education, models and modeling have played very important role because we don't have a real system in our eyes. So it's very important to learn chemistry in a laboratory environment and so on. So the role, chemistry has also played a very important role in vocational education and informal chemical education. So chemistry is a central science despite what other subjects will feel. But what is important is the chemists themselves have to realize that chemistry has changed from structure-driven chemistry to function-driven chemistry. The old days, chemistry was about analyzing structures. But today, what is important is to look at the function that you want to do and then find out the molecule. So it's a retro thinking that is going to become extremely important in chemistry. You have to break the traditional barriers of chemistry, organic, inorganic, physical, biochemistry, and so on. Because it's very important that to understand that chemistry is interdisciplinary. Chemistry also has to be driven by emerging trends in research, technology, and also by societal needs. I think I will talk about a little bit of societal needs. What are the emerging trends in research? What is important, I think, is to teach history of science as a curriculum. You know, in universities like MAKAUT, which are new, must start. IITs have started. IITs still have, in some way, history of science as a curriculum. Though I think it should be strengthened. There are not too many good teachers, I must say, to talk about history of science, like how did Archimedes discover, how did Newton discover, Einstein, Avogadro, Faraday, Lewis. What is interdisciplinary science? For example, Archimedes, who comes into physics, was a great mathematician. Many of you know. So I think there are several examples. Newton himself, of course, was a great mathematician who did Principia Mathematics, calculus, and so on. But it comes in the physics. Same way, Michael Faraday, G.N. Lewis. There are several examples. Then historical research. For example, I am not qualified to talk of everything because that will be a very long talk. But from chemistry, I can bring out some of the very important discoveries like oxygen. You know, you cannot imagine life without oxygen. But oxygen was not known before 1770s. Atomic theory, molecules, Avogadro's law, urea synthesis. I talked about urea synthesis. Benzene, I talked about the dream-based synthesis, periodic table, electrolysis of Davy, very important. Humphrey Davy is a great person. Electrons, I think you have to understand, I have not written here battery, but what is interesting is battery was discovered in 1800 and electrons are discovered 100 years after. And today we think the conductivity is due to electrons. But battery was known 100 years before the electrons. How did that happen? I think that's the history. Radioactivity, plastics, polymer, core theory, chemical bond, and of course, all the quantum theories that has contributed not just to chemistry. Physics is a modern way of understanding science. So I think the history of science is a very important part in the curriculum. And I think all universities must try to impart them to the students to how to do research. I talked about the future challenges, and I just give a few here in this slide of renewable energy, sustainable resources. Renewable energy, all of us know that the energy, fuels, and all that are going to end. So it's very important to have renewable energy in the as a very future challenge. We must have sustainable resources. I hope all of you understand what is sustainable. Sustainable resources are resources which do not deplete because we consume. So solar energy, for example, is a sustainable resource. There are many others that I will talk about. We must have processes which are energy efficient. Again, it could be a chemical process, it could be a physical process, biological processes, but they must be energy efficient. We must have processes which are environment friendly. Today, it has become very, very important, particularly the COVID, that we must protect our environment. We must protect the environment from pollution. We must protect our environment from virus. So we must have environment friendly processes. So when you restart, I think it's going to become a very important part to realize. We also need healthcare. And I think, again, COVID-19 has made us aware that not only we need drugs or vaccines, we need them affordable because the poor people who are being affected. So research, the challenge is to get affordable healthcare. Cultivation of farms, I think this will never be overstated. Minimum land water, maximum crops. Technologically enabled defense systems, again, a lot of challenges are here. And many of these, if you solve any one of these, it requires interdisciplinary expertise. A chemist cannot solve alone. Neither can a physicist solve. It requires chemistry, physics, biology, mathematics, very importantly, geology, as well as engineering. Many of these will require very good engineering skill. And that is the reason many IITs are realizing that maybe engineering is something that we lost, that we didn't want, is still important. It is not that science should exist in an engineering institution like IITs, but I would say engineering should also exist in a science institution like IIT. And I think that is the reason even some of the IIT like Bhopal, they are starting engineering. We are also discussing, at least we have started computer science, data science, and data science as a minor discipline. And I think in future, we will see how engineering can be integrated. I talked of renewable energy and sustainable resources. These are some of them. So, solar energy. India has sufficient solar sunlight storage. How do you convert them to heat? How do you convert them to electricity and other usable forms of energy and chemicals? That is going to be a big challenge. Wind energy. That's a very important challenge. Wind is also sustainable resources. If those who have gone to Europe particularly have seen, like in places like Netherlands, Holland, so many things are running on wind. Fuel cell, this runs on hydrogen. And here I must say that hydrogen can be a sustainable resource. Many people used to worry how to get hydrogen, but that is less of a worry today. The question is, how do you use hydrogen for running a car, for example? So the real challenge there is to store hydrogen in a reversible manner. And I think that is something that people are looking at. Bio-waste, there is so much of bio-waste from everyday home, everything. Can we not use them to alcohols and chemical fuels? So, or even value-added chemicals in general. I already talked of fuel cell, and that actually brings me to hydrogen energy. We have nuclear energy, but very importantly, carbon dioxide into fuels. Today, a lot of work is going on, reduction of carbon dioxide into value-added chemicals, so that once environment is also saved and resources come up. And this can be sustainable because CO2 production is going on. Despite all our efforts to reduce it, it's also going to go on. So can you not convert them into energy, sources of energy? Challenges of COVID-19, challenges that are thrown. We have to do research to combat environment, climate. We have to bring in now technological innovation more than before. In fact, the very fact that the webinars are taking place is a technological innovation of some sort. Webinars existed even before COVID, but now people know that it is very, very important. Many meetings are taking place completely online. So people are able to bring in technological innovation. And I'm going to talk of teaching, of course, more digitalization. So you have to have a digitalization. Of course, education, online teaching. And we have been talking about the online teaching all the time today. So teaching on a digital model has a big advantage. You can teach anytime, literally anytime, literally, anywhere, to anyone. And of course, the anything is a paraphrase, but the question is that you can do a lot, just like you can go and teach today a student in Stanford, Caltech. They can also attend your lecture, which was not possible before. So imagine the COVID-19 has put up a lot of challenges, and those challenges have opened up large opportunities. We are all worried about how to do online teaching. I'm going to come to that a little bit later. Although I'm not going to go into details of that. Details are being covered by many other talks, just like I told in IISER Kolkata today, we had a talk. But I'm going to talk a little bit about how opportunities are thrown up and what are the problems. So lots of technology-enabled tools have to replace hands-on experiments. Whether doing experiments in laboratories is also going to become a problem. So the immediate future need would be probably to use some technology-enabled tools. So I think these are some of the challenges that the COVID is throwing, apart from the research to protect environment and climate. So in the new normal, I hope you understand what I mean by new normal. When we open after the COVID, we have now opportunities to have innovative solutions. We must open research in a way that we do not pollute the environment. So this is an opportunity when you restart. It's basically an opportunity to restart. Can we restart in a proper manner? Of course, the thrust of research will go to virology. That's very important. Immediate thrust will be to pharma, to get medicines, vaccines. Thrust will be on very, very smart materials to make life easy. I hope all of you know what is smart materials. They are basically man-made materials which have sensing and actuating characteristics of natural world, like plants, for example. But they are man-made. The materials are man-made. So that's why they call smart materials. So those they can make life easy. Communication of subjects, innovation in education, innovation in laboratories. So that would be very, very important when you become the new normal. Let me tell you a little bit about online teaching, a few 3 or 4 slides. I'm not going to really develop a lot on that, but we have to develop online learning plan. And more importantly, a continuity of learning plan, because students will go from one class to another class. And during the COVID, just like now it's happening, there is a continuity. One semester is over, another year is starting, and so on. Teaching strategies, and I think everybody is talking about teaching strategies. Platform, you do iPad, writing on the whiteboard, maybe a whiteboard in front of a camera. I'm not going to go into the details. So many strategies you can use. Communication rules. People are also saying that when you do online teaching, you have to follow certain disciplines. What are the devices, solutions, policies? I think that's also very important. The government, states have to have policies to support online or even what I call blended learning. But important thing to remember, keep the plan as simple as possible. Don't make it too complicated. Make the expectations clear for the learners, because this is something people should understand. The students must understand. What are the expectations? Computer-intensive tools. I have been telling the integration of research and education by computer. They're essential to be used. But I think I want to add this. Let's not forget that we still need to teach. I think many people, I must say, when they do online teaching, they're obsessed about the computer. They're obsessed about writing, they're obsessed about writing equations. They're obsessed about showing diagrams. But let's not forget that we need to teach. And teaching is not just content. Teaching is about explanation. And we are worried about how to throw the contents by PowerPoint presentation, etc., etc. But you have to explain. That part has not gone. You have to connect themes. That part has not gone. And I always say, most fundamental reason we teach is to inspire. A good student can get many things, but a good student has to be inspired. And I think this is a very, very important part in a classroom teaching, which you should not forget when you go to online teaching. Despite all the trouble, despite all the tools that you use, I say this, let's not forget that we still need to teach. And teaching is not just assembling tools to provide contents. And I think this is a very important part of online teaching. I talked about online learning or teaching, continuity of education for emergency learning and teaching. That's very important. It's focused on the transition of students from one type of learning to another, because their context is changing. Somebody is going from class 12 to college. Context is changing. How do they transit? And I think one has to worry about that. Continuity of learning plan do not only involve the technologies to be used, but also considers how the students will return to the campus. And that's very important after the emergency ends. So one day COVID-19 will end. The students will come to the campus. And I just look at this website. There much details are given here. How the students will return, and that is a part of the continuity. Program communities, sharing experiences. This is very important. There are so many people who are doing online teaching, schools, colleges. They should share their experiences. And that is not happening at this point. Several institutions should come together. What is their experience? It is not that sharing experience within, but sharing experience from one school to another school, one college to another college. Podcasts. Podcasts can be used to share stories of school closures. What is happening? Facebook groups. Of course, Facebook group is very, very important. Lots of schools, information technology leaders, they have become very popular in Facebook. So groups have to be formed. Twitter, of course, these are known, but now we have to use them properly. The web chat, posting ideas, and so on. One of the two important ways of teaching, and I think I must mention, is what is called synchronous and asynchronous teaching. Synchronous teaching is basically what happens collaboratively and at the same time with a group of online learners. Usually there's a teacher and there are students. Asynchronous teaching, it can happen anytime, not necessarily in a group. Maybe there is a teacher feedback. So our problem is not just to do an asynchronous teaching or a synchronous teaching. Many times we discuss, oh, let's have asynchronous teaching because synchronous is very difficult because of internet and so on. But we have to look at both the options because both of them have their own virtues. The goal is not necessarily to recreate a face-to-face classroom, which you are aware. Many of us are obsessed by looking at face-to-face classroom. So online teaching, online learning will also provide opportunities for them to work more independently and learn to use tools and strategy that they otherwise may not have learned. So that's very important. We have to innovate. We have to be creative, resilient, and I think that is very important. Many of us are losing this in online teaching because we are becoming impatient. We have to be resilient and very fast we have to adapt. When you do something that suddenly happen, my internet may go off, and I again tell you, my internet can go off right now because there may be a power failure. We have a generator. It takes a minute or two to come back to the generator. You will lose me for those 2 minutes. I have to reconnect. Okay, this is a good time to tell you that in case that happens. Just wait. So adaptation is very important. A fast adaptation is required. So we use, of course, computer-aided tools, and whether you go to Google Meet, there's so many tools, platforms to teach. So at the same time, when learning is computer-aided, COVID research is also giving rise to renewed interest in computer-aided research. Not that the computer-aided research was missing, but I'm going to change gear to research now. As all of you know, that COVID itself is being analyzed by data analysis tools and simulation. So many people are simulating, so many people are analyzing when the peak will come, when the peak will go. And every now and then you see the analysis has its own challenges. And just recently I saw some experts said, oh, first week of September, or sometime in the middle of September, India will have its peak. We don't know. The peaks are changing. But I think the computer has come in the front. We are also looking at a biological simulation of virus from the first principle. So there are two kinds of computer that I'm talking about. One is for data analysis, which are simply mathematical tools. Another is physics, whereas physics-based principles are used for simulation. Pharma research, there will be a physics-based, there will be a data analysis. I will tell about that a little bit. And the COVID-19 has brought computing tools in integration of thoughts. That's very important. Thoughts are integrated. For example, I talk of computational science. This is physics. You need a solution. I need to break nitrogen, make nitrogen to ammonia. I want to convert CO2 to fuels. Those are my challenges. I need a solution. Of course, you do experiment. You do theory. Many chemists, many physicists, biologists mind the theory. And then there is a computation. I repeat, computation is not theory. I hope all of you know this, but I repeat because this is sometimes people forget. Theory, experiment, and computation are three important sides of a triangle to provide you a solution. What we need is neither theory, nor experiment, nor computation. Separately, what the society needs is a solution. And that is where integration of skills, interdisciplinarity is very important. But what I want to tell, computation is a very important part of this integration today. Let me talk about computation. Two important quotations by Cotele, 200 years back, 1828. The more progress physical sciences make, the more they tend to enter the domain of mathematics, which is a kind of center to which they all converge. We may even judge the degree of perfection to which a science has arrived by the facility with which it may be submitted to calculus. And brilliant science and mathematics cannot do without this. Let me now show a code which is in the context of chemistry. I think the context should not have changed, but you see the change of the context. A. Comte in 1830, it says, every attempt to employ mathematical methods in the study of chemical questions must be considered profoundly irrational and contrary to the spirit of chemistry. Imagine, contrary. If mathematical analysis should ever hold a prominent place in chemistry, and it says it's an aberration which is happily almost impossible, if it does, it would occasion a rapid and widespread degeneration of that science. So just imagine how the chemist's view of mathematics and computation 200 years back. That mathematics has no place in chemistry. It is happily proved to be a wrong statement. Even biology has huge role of mathematics and computation, but I have to tell you this and this, both coming within 2 years. You can imagine. So it's very important for me to take this both, but you know what I believe. I don't believe the second statement. So computational chemistry and biology have become very, very important. The physics, it was always there. So I'm highlighting in chemistry and biology, the theory comes from physics. Of course, the physics is what is driving everything. Using the physical theories, computers, algorithms, we now solve complex equations from the theory. That's very important. We predict in computer structure and properties of molecules. I think it's very important. We predict reaction between the molecules. If the reaction takes place, if it takes place, how fast it takes place. We predict dynamics of an evolution, and that is very important for both chemistry, physics, and also for biology. How does a system evolve? I will talk about that a little bit. We also model new materials and design drugs, and of course, biological activity. Look at the biological activity. They are also modeled today by computational biology. Many of these is not just physics-based. Of course, it started with physics, but many of these are using simple mathematical tools where data, a lot of data, which either comes from the theory or comes from experiment, is analyzed by a simple mathematical tool, artificial intelligence, machine learning. Hopefully, this analysis will bring a new physics. And I think this is very difficult sometimes to expect. How do I get a new physics without doing a physics? But it is possible, and that's the hope with which data science is moving. But data science certainly makes simple to at least analyze the data, which by itself is a very important part. If the data science eventually gives a throwback to a new physics, that will be great. But I think artificial intelligence and machine learning are going to play very important roles in the theory, in the development of this area. And of course, I must say, when you talk of theoretical chemistry, we always are obsessed with the quantum chemistry today, modern quantum chemistry. But let's not forget that G.N. Lewis talked about valence, tautomerism, before quantum mechanics formally came. You look at the years, those who know the history of quantum mechanics will remember that the first paper of quantum mechanics by Erwin Schrödinger came in 1926. G.N. Lewis talked of the octet rule, which makes a molecule stable, 8 electrons around an atom. In a very famous paper, look at the title of the paper, The Atom and the Molecule. I can't imagine such a fantastic title in a Journal of American Chemical Society, 1916, by which, of course, Erwin Langmuir, and I think G.N. Lewis was very upset that Erwin Langmuir in some way stole his ideas to make what is called octet rule, again published in Journal of American Chemical Society, 1919. I must say there is a lot of history. Again, history of science is very important. When this happened, G.N. Lewis had gone to the World War I. Many of you remember World War I had started. At that time, there was no internet, there is no Google. So G.N. Lewis did not know that this paper was published by Erwin Langmuir. When he came back in 1921 or 22, he was aghast. He was shocked. He wrote a letter to the editor of the Journal of American Chemical Society. How could you allow this paper to be published? This is my idea, the octet rule. And I think there's a very nice history fight between Lewis and Langmuir. I think all of us who are interested should read the history. It's very interesting. I'm not going to go into that. But with this, what happened? The chemistry started. The quantum mechanics came, quantum chemistry came, and eventually people started developing various kinds of theories. People still realize that the classical theories are important, but people began to understand that why classical theories can be used for large systems. Because they're large systems, you can freeze the degrees of freedom. So came molecular mechanics, where only atom-atom forces were taken. Came a combination of these two, which won a Nobel Prize in chemistry in 2013, QMMM, very important method, but one system has quantum mechanics and classical mechanics grafted. Then, of course, beyond an atom, we go to coarse grain simulation, where bits of atoms are there, group of atoms are there, they're interacting with another group of atoms. So now I can do very large system because I'm basically freezing the degrees of freedom. And that is what is written here, that the philosophy of multiscale method is to use knowledge of a more precise description at smaller length scale, to model approximations at the larger length scale. So this is very important philosophy. A precise description at smaller length scale to model approximations at the larger length scale. Coarse grain simulation is one such idea. So many active groups are there in India who I'm very happy, who are working on molecular mechanics, quantum mechanics, coarse grain simulation. Many groups in universities, state universities, IIT, of course, ICERs, NITs, several places. And this is very good for the country that the computational science has been developing. Of course, when you talk of quantum mechanics to classical mechanics, it is nothing new. Niels Bohr had said it long back. By its correspondence principle, in the limit of h going to 0, quantum principles go over to the classical. And that's exactly what happens for the large systems. We now know how to model these potentials. And that is the philosophy by which we have gone from atoms, molecule, cluster to nano, and eventually to the bulk. We don't use the same method. You don't use for this table where I'm putting my laptop right now, you don't use quantum mechanics. But let's not forget that this table also consists of electrons. But we don't solve the Schrödinger equation for the table or for the building. So this is very important to understand how from a small atoms and molecules you go to the classical, and that's what I call a bottom-up approach. So define theories at different lengths. So this is a very important slide. In fact, this tells you horses for the courses. Depending on what is the course, I'm going to employ the method. So I have a quantum mechanics, which is basically ab initio method. Full quantum mechanics at small length and time scale. Then we have proteins, nanometers, where you do molecular mechanics, atom-atom simulation. I'm going to talk a little bit about that because biology is very, very important. And today research in biology is inspired because of COVID problem. So I'm going to talk a little bit about that. Then you have an even larger length scale. Polymer, for example, use mesoscale simulation and eventually engineering simulation. Interestingly, this got developed much earlier. This came later and people started connecting. What would be ideal? Sorry, what would be ideal if I know how to go from here to here by freezing the degrees of freedom? That's a very tough theoretical problem. People are looking up to mesoscale. Can somebody say how mesoscale simulation go to finite elements, CFD, Brownian motion? I think it will be a great theorist will be able to do that connection. That connection is very, very important. Central theme of computational chemistry or biology, molecular biology, is to start from a structure, look at the dynamics and the reactivity, how the system moves, and the same in molecular biology, structure, dynamics, and function, except that there is a sequencing on top of the structure, and then there is evaluation from the function. I evaluate from the function whether it's a good system or not in biology. But this is basically a central dogma or a central theme. When you do computation, particularly I'm talking of chemistry and biology. So when I say chemistry, of course, it also includes biology, and physics is, of course, always there. So I don't have to say. So we have quantum mechanics in the small length scale. I just paraphrased by the Schrodinger equation. That's completely physics. You have molecular mechanics, classical force field, and then you use Newton's law. Again, physics is always there to do a dynamics. And then, of course, there are methods which are completely empirical. Data science. I talked of data science, which is not physics. Statistics, not physics. And they are called QSAR, quantitative structure activity relationship, and similar methods which are widely used in clinical and medicinal chemistry. How big systems can we deal? So I'm now talking a little bit shop. I'm talking shop to my fellow chemists. If you use ab initio methods, let's say in a computing setup, I can do 100 atoms. Let's say, assume. In the same setup, if I use quantum mechanics, which is still here, but what is called density functional theory. I don't want to go into the details right now, but this is not solving the Schrodinger equation. Here you write energy as a functional of density, so it simplifies. Ab initio is where you solve the H psi equal to E psi or H psi equal to IS plus del psi, del T, whatever. So in the DFT method, on the same setup, you can typically do 1,000 atoms. With the semi-empirical method, where the integrals, where it is not fully ab initio, again, I will not go into the details, you can do 10,000 atoms. If you do molecular mechanics, you can do 100,000 atoms in a typical setup. So you can see if you go for a large system, your computing setup is not very large, you'd rather like to use this. And that's what exactly happens for protein. Why do you think biologists use molecular mechanics and not quantum mechanics? Because it's just not possible to solve. And one very important thing is what is called computational scaling. So when you are doing this physics-based computational method, we can actually estimate how do they change its size. The CPU time changes its size. Suppose a calculation scales as n to the power 3 for some n equal to 10, whatever the n units, and it uses 1,000 seconds in a computer, which means 17 minutes, a cup of coffee. 17 minutes is what you take a cup of coffee. So you take a cup of coffee, the calculation is over. On the same thing, if you use DFT, it goes as n to the 4. I'm just telling you, no proof, I'm telling you. It would require a French dinner. 10,000 seconds, which is typically 2.8 hours. You can go for a French dinner. I hope all of you know that French dinners are long. You can come back, the job is over. If you do second order Laplace, again, I will not go into this. This is a slightly correlated quantum calculation. You get into the 5, that would be more than a day. I have not written it. If you use what methods that we develop, couple cluster, you may go to a vacation in Kerala and come back. So you can happily submit the job, go for a vacation and come back. So I think that is the way the computer time increases, and many students do not realize they become extremely impatient that why my job is not getting over. Because quantum mechanics is difficult and molecular mechanics often oversimplifies, we have methods which mix both quantum and classical in a complex environment. So these are called QMMM method. So for example, let's take a biological system, and this is typically in biology it is done. And you have a central point where a drug attacks. So this is, let's say, membrane or whatever. A drug membrane interaction cannot be discussed without quantum mechanics because its interaction energy is very, very small. And don't forget, drug is a chemical molecule. It's a molecule. So you cut out the blue region around the interaction, a small region where you use quantum mechanics, which is chemically active part. Then you have an interface region, and this is where people have to do some jugglery, how to tailor it. And then you have a large environment outside. So this is classical molecular mechanics. The blue region is quantum mechanics. And then this is where you try to match quantum mechanics to molecular mechanics. So there is some link atoms and there are technical details which I'll not go into it. But important thing is now I'm able to do large system, yet where required, I'm using quantum mechanics. Quantum mechanics is required only here. But my molecular mechanics is allowing me to describe the large systems in a seamless manner. So that's the idea of doing a mixed calculation, not just quantum mechanics or molecular mechanics. So again, horses for the courses. I actually put, this course is so complex, I'm putting two horses. One quantum mechanics and then molecular mechanics. So I hope all of you know what is horses for the courses. It has come from the golf, not from the golf, from the horse racing, where depending on the course, you employ the horse. Of course, the most coveted method in quantum mechanics is what I told, the couple cluster, which is n to the 6 minimum. And there has been 50 years of couple cluster from the original landmark paper of Jerry Chizek in Journal of Chemical Physics. So many things have happened, and these are now called, with triples, it is called the gold standard of quantum chemistry. There are, of course, multi-reference methods which can do excited states and so on. I will not worry about it, but I thought I will just say that there are several people who have worked on couple cluster, including our own group, and we are also involved in the first general purpose code. And this actually gives a very important connotation of a model theoretical chemistry, which is very often said getting right results for the right reasons. I think this is a very important part of doing theory. You just do not want to get the right results. You want to get right results for the right reasons and not the wrong reasons. However, since it is very expensive, very often today's research is based on density functional theory. DFT, it is usually the method of choice in materials because the energy, now the Schrodinger equation is not solved. Energy is expressed in terms of three-dimensional electron density. The problem here is that although it is in principle it is exact, you don't know how to get both exchange and the correlation functional, and neither do you know exactly how to get kinetic energy. So of course, with constant kinetic energy, some approximation of exchange correlation functional, people are now beginning to use DFT in a big way, dispersion correction, basis set. They're trying to speed up. It's a very good choice because it's typically n to the power 3 or n to the power 4, whereas couple cluster, even singles, doubles is n to the 6. So I already told you what's the difference between n to the 4 and n to the 6. So that's going to kill. But if you look at DFT, it's not always very reliable. So for example, I have given very simple numbers of enthalpy changes from methane, organic molecule, methane to methylene plus hydrogen and so on. These are the experimental enthalpy calculation, delta H in kilojoules per mole, very simple thermodynamics. These are the couple cluster, singles, doubles, triples, on the money, as you can see this, all the numbers. If you do Hartree Fock, which is one particle potential, just like the simple mean field calculation in physics, you see the numbers are not good at all, not even the sign. Numbers are not good. If you do G2, this is a very good method. Numbers are pretty good. They're not as good as couple cluster, singles, doubles, triples. If you do DFT, you can see the problem. Some numbers are very good. Very good. Some numbers are not so good. Not so good. Not so good. So the basic principle, basic message that I'm trying to get, that DFT is good, but not always reliable. But it is a low-cost solution. So people have to understand that is the reason DFT is very much popular. Popular for many things like clusters and solids in particular. But for atoms and small molecules, quantum mechanics is used, using Gaussian or even for cluster. We use methods like MP2, couple cluster, CAS-SCF. I don't want to go into detail. But for periodic solids, where periodic basis sets are used, DFT is often the method of choice because it's very large. Clusters also DFT are used. Catalysis, design of catalysis, computational design of catalysis. I must say that many of my chemist friends are working on this. And I'm also doing a lot of collaborative work on computational catalysis, where, so this is, for example, the points that we are designing the catalyst. There are so many things which have to be done in the catalyst designing, and many of these now can be done by density functional theory. Let me very quickly go through this. I not want to talk short, but for biology, people use not only the force field, but also they use this force field, which is basically harmonic, plus all kinds of short range potential like London, Lennard-Jones and Coulomb interaction. Using this force field, they actually calculate the force on the nuclei and how the nuclei are moving by classical molecular dynamics. So this is basically Newton's law that they solve. This is very simple. So nuclei move by Newton's law. Electrons are not considered explicitly. So it's the atoms which actually directly move. It can be even extended at a higher length scale like mesoscale, when group of atoms will be replaced by group of atoms will replace atoms. But with appropriate force field, one can do very large systems like protein folding, it's a very important problem, polymer simulations, and so on. People are also looking at ab initio molecular dynamics, where electrons are explicitly considered through quantum mechanical calculation, but the nuclei are still classical. So there is a mixture of quantum mechanics and classical. So force on nuclei are come from electrons, quantum mechanical density. Density gives you potential or force, and then the nuclei move. There are two kinds where electrons and nuclear motion are coupled. They are called Carpariniello molecular dynamics. Where they are separated, this is called Born-Oppenheimer molecular dynamics. This is also becoming very, very important today, and many people in the cluster physics are using it. Of course, there is another kind of molecular dynamics, I would not say molecular dynamics, where even the nuclei are solved by Schrodinger equation. So here, if you see both nuclei are classical, the question is whether electrons are there or not. But where nuclei are also solved by quantum mechanics, that is called full quantum molecular dynamics. I'm not mentioning because really for biology and even chemistry, not much can be done with this. Of course, people are doing for small molecules. There are groups in India who are working on this quite well. And there is a group at IITs Kolkata also, where Satyajit Adhikari is actually working quite well on the quantum dynamics. There is a group in Hyderabad University, Susanta Mahapatra, and various people, my friends are all doing. Let me now quickly come to what we are doing on highly correlated electronic structure methods. So basically, again, our philosophy has been to get right results for the right reasons. And very recently, of course, I'm only talking about recent work, we have been working on relativistic coupled clusters. So much of our work is actually physics. It comes in physics journals as well. We identified very important molecules like mercury hydride, radium fluoride as a parity time reversal violating interaction, plasma effects, electron nuclear scalar pseudo scalar interaction. In fact, these two papers are just published this year. Then we are also using bound state coupled cluster methods for resonance and decay problem. This is again a physics problem. Physics people would use time dependent methods. We are actually using bound state methods, but in a way where the Hamiltonian is made non-Hermitian. So non-Hermitian quantum mechanics is used where bound state methods can be actually applied, and then one can find out from the real part of the energy resonance position, and from the imaginary part you can get weight. We are doing electron molecule resonance, OJ decay, interatomic Coulombic decay, several such work. I'm not going to go into the details. And this is, of course, the catalyst designing, which I'm doing collaborative work with one of my collaborators in Pune, Vidya Osare. I think it's a very good work that is going on. There I'm using DFT in the main. We are also working on small clusters like gold and silver, very, very interesting properties these clusters have shown. For example, 8-atom gold cluster is inert, but a monodot, a silicon monodot AU7 is AU8 is catalytically active. Pristine gold cage is not so catalytically active, but they get activated by metal inside the cage. Hydrogen chemisol gold and silver clusters are also very good for oxidation reaction. We have also looked at aluminum cluster for dinitrogen activation. One of the very important cluster, and I hope some experimentalists will be able to synthesize this on a small aluminum cluster on boron nitride doped graphene. So we have predicted if you have a graphene support and dope it with Bn molecule, not B, N. It's a boron nitride molecule, and then put aluminum cluster. This can be potentially good catalyst for bond activation. And if you can break nitrogen, that will be great. But we have already tried good for activation, nitrogen, oxygen, any carbon halide bond, and so on. So for example, I talked about AU18. One example I'm showing what kind of things we can do. It's a CO oxidation reaction. CO plus O2 going to CO2. It goes from a reactant to intermediate, transition state, intermediate, transition state, back to product, finally. With a barrier of 0.71, 0.45 eV, with the AU18 pristine cluster. Look at the same work when I put sodium, potassium, magnesium, and calcium. The barriers drop down significantly. If you look at the CO oxidation reaction with chemisorb cluster, like AU6, AU8, you can see as soon as I do hydrogen chemisorption, barrier goes down. Barriers are very high with the pristine cluster. So I think we get enhanced oxygen activation. So many of these clusters, if they can be synthesized, it's very good. We talked about hydrogen storage. I looked at a lot of work on metal organic framework. One is a physics option, so you have to actually make them stronger. The chemisorb one, you have to make them weak. We typically don't need either of these two, but something in between. So doping has been used as a strategy. Potentially good catalyst we have found within MOF is a scandium decorated MOF5 or ZIF, zeolite imidazole framework. Again, what I'm trying to show that all these, why am I showing all this suddenly? All these are simply done by computer. A computer-aided research is able to explain and predict many things. For example, fuel cell. These are something that are running in fuel cell. A computer-aided computer science, computational science can actually do artificial photosynthesis. We don't know what catalyst is required, but people are trying to model the photosynthesis in computer and can give. So same way today, people are working on COVID virus, the simulation of virus. So where computer is giving up in education, they're also coming up in research, and they're trying to integrate these two. We can show a lot of good research by today online teaching. With online teaching is computer. So of course, LEDs, all of you know the LEDs like silicon themselves are very poor conductors, but because you dope them by group 3 or group 5 elements, then they become very good conductors. And their LEDs are used everywhere, into traffic light, blinking, jewelry, flashlights, blinking jewelry, so many things. So the color depends on dopant. Again, very beautiful thing, but we can computer model it today. So this theory has come that good. Nanomaterials. You have to talk of nanomaterials because they're very important catalysts. Very, very famous statement of Feynman, plenty of room at the bottom. 8 years after Richard Feynman said, you can't play with an atom or a molecule. Don't forget 1952. Erwin Schrödinger said, you can't play with an atom or a molecule. Schrödinger said in 1952, and then you look at Feynman, plenty of room at the bottom, 8 years after. What is the most significant discoveries of nanomaterials? Many people ask me. I say electron microscope, STM or AFM, and fullerenes. Both of them got Nobel Prize. These are the major discoveries of nanomaterials, and today nanomaterials are used very importantly in many places. Before I end, I must say that I talked of physics-based computation. I would talk what can be done simply by data science, and that is very often called informatics. So there are two phases of computational science, informatics and physics. So I think they have to meet in some way. So many times the problem is very difficult to solve. So we build a purely empirical model to predict the molecular properties from chemical structure using available data. And that is where data science comes in the picture. That is where informatics will come in the picture. So informatics represent a phenomena mathematically, but not in a physics-based way. And it's a very provocative statement that I'm making. Inputs and output models are based on empirically parameterized equation or more elaborate mathematical model. We don't attempt to simulate the reality, but it has a very high throughput because it's very fast. So one of the major things that is done in chemo and bioinformatics is quantitative structure activity relationship, empirical. There are lots of nice informative techniques are used today in drug discovery, because drug discovery is so complex that beyond a point, you have leads, but you still don't know which will work. And then QSAR takes over. QSAR predicts, and then experimentalists take over. Then there is a testing, etc., etc. So I think it's very important that the two phases must go together. The physics and the data science must go together. I will end with these slides of, again, emerging areas. In particular, I will mention one, the rest of them I have already talked, synthetic biology. The synthetic biology is becoming very, very important today, where we learn how to do laboratory experiments inspired by nature, inspired by biology, how nature is doing things simple. The photosynthesis is one example. Our body enzyme catalysis, how do they do what? Can we do this here? Can we make nitrogen to ammonia? Inspired by biology. Biologists are also learning chemistry to understand. And I think on both fronts, synthetic biology is advancing. It's a very important area, and I believe this will be a very important emerging area in many. I know most of the Indian institutions have not gone to synthetic biology in a big way. So I think we have to do that, including in ICERs and so on. And I think it's a very important area to work on. I will not worry about nanotechnology, everybody knows. But I just want to say that many people don't realize that the hydrogen atom is only 0.04 nanometer radius, whereas proteins are about 20 nanometer. A human hair is 10 micrometers. So you can imagine 10,000, 25,000, 250,000. How small is a hydrogen atom compared to human hair? I think we don't realize, and it is amazing what microscope has done today. And I think that's a very major thing. That's the reason I just wanted to show the length scale that is there. This is one example where people are looking at protein particles by coarse-grained molecular dynamics simulation. Just one example I have brought. People have done, these are coarse-grained beads. So it's a coarse-grained simulation, not atomistic. 36,000 CG simulation representing 500,000 atoms. So it's possible with coarse-grained simulation at various different time scales. They have gone up to 4,000 nanosecond, with a 25 femtosecond time scale. Of course, time scale is also very important, but you can't take half femtosecond because you have to go to a very large time scale. Of course, these are people who are technically using they will understand what I'm saying. But I'm saying this is possible today. So the COVID virus is quite likely there will be a lot of work in computational by computer, but they will analyze this. I will end with this last slide on what all work I'm doing. Of course, I already talked about certain works like catalysis. I talked of some work on the electronic structure, hydrogen storage, and so on. But this is just to give you a final slide of all the areas that we have been doing, starting from NCL to IIT Bombay to IISER Kolkata. And I hope I can continue to remain active. I must end with acknowledgement of various sources, particularly in the part of education, the site that I quoted from Australia for some of the online education. And of course, many of my students, my collaborators, some of them I mentioned, many students. I don't want to mention each of them, from NCL, IIT Bombay, IISER Kolkata, and collaborators from SP College. And thanks to SERB, DST, Indo-European Union, CSIR, Indo-French Center, Board of Research, DST DAT, I don't know, CDAC, I miss CDAC. So many funding agencies who have funded me in my whole life. And I have many projects from SERB, DST, Indo-European Union, and so on. Indo-French also had 2 projects. So I'm very thankful to all the funding agencies for providing me a career. And I thank all of you for hearing. It has been slightly longer than an hour, maybe an hour and 15 minutes. A little bit sorry about that, but thank you for your attention.
Thank you, sir.
Yeah, if there are any questions or something you're taking, I can take up.
Yeah, sir. Sir, we will move to the discussion and question.
Yeah, your voice is somewhat low, I think. I don't know why.
Sir, can you hear me now?
I can hear, but very low voice.
Okay, sir. Sir, we will move to the discussion and question answer session just in few minutes. Just let me thank you, sir. And it was a mesmerizing session of last 1 hour or so, capturing everyone's complete attention. And it's so much informative and elaborative talk. And I must say that there was not a single corner of scientific area that you have not touched upon and discussed so understandably that everyone can have the knowledge and the role of computation as an intensive tool in every aspect across all disciplines. The opportunities lies in the science, in academic institutions, research labs, uh, maybe the mission driven projects, and how the evolution of scientific discoveries through the curiosity, necessity, and discussing all the aspects of those things. And definitely the future challenges that lies ahead in time after the COVID-19 situation, and the opportunities that we can have to incorporate the computational tools into our teaching learning methods, and as well as to implement these in the research areas. And thank you once again, sir, for sharing the information with us about the brilliant ideas and endless opportunities that lies ahead. And undoubtedly, all the participants, be it the students or the researchers or the faculties or practitioners of science and engineering across all disciplines, they will take a lot of information with them and explore them in their individual fields of expertise from the knowledge they gather from your lecture today. So thank you, sir, again. Now I should like to move to our director of our school, Professor Shukhendu Samazdar, to share his thought about the webinar. And just then after his remarks and thoughts, we will move to the discussion and question answer session, which will be moderated by Dr. Bag. So over to you, sir.
Namaskar, Namaste, Honorable Vice Chancellor of MAKAUT West Bengal in absentia, Honorable Director of IISER Kolkata, distinguished panelists, respected participants, and members of the borderless knowledge community. The topic of today's seminar on the web is Transforming Science Education and Research Through Computation, Intensive Tools of Learning. The implications in depth and breadth of the topic is daunting, and especially I have been positioned to speak after a stalwart in the field, Professor Saurabh Pal. So I take up the microphone in utmost humility. Maulana Abul Kalam Azad University of Technology, West Bengal, is a state university which has jurisdiction over the entire state of West Bengal in terms of technical, management, and professional education. It has more than 150,000 students in its care, studying in 200 plus affiliated colleges and about 100 in-house programs of the university. The university started essentially as an affiliating university with affiliating colleges. However, particularly under the dynamic leadership of the current leadership of this university, a transformation process has begun. And MAKAUT has introduced a large number of in-house programs in the undergraduate as well as in the postgraduate level, thanks to the forward-looking position and directive of our Honorable Vice Chancellor. In this way, the university is now morphing from an affiliating university to a complete university, in the sense that it has both in-house program and affiliating colleges. Now, the emphasis of this university, of the leadership, is on computational and computational sciences and application of that in all the domains of the science. It is basically aligning with ourselves or the university with the time, with the trends of the time. For example, in the school that I belong to, which is the School of Natural and Applied Sciences, we have introduced programs in the Department of Material Science and Engineering, which is MTech, which is MSc, as well as BSc in Material Science. Now, there are not too many institutes in India, let alone in Eastern India, which offers undergraduate programs and graduate programs, BSc and MSc in Material Science and Technology. Now, here the emphasis is on computational material science and nanomaterials and emerging materials. Also, we have departments of forensic science. That is a rather important area. That is, it is increasingly taking becoming critically important because of our the cybersecurity issues, and our lifestyle is changing in such a way that forensic is not just about crime, it is about many issues, and the university leadership, recognizing it in time, introduced a department of forensic science, which is also emphasizing on the computational aspect of it. A few weeks ago, about a month or so ago, it had hosted a webinar on steganography, where a lot of computational techniques are used in reality. And the Applied Sciences Division also has a master's program in applied chemistry, which is emphasizing on computational chemistry, as well as there are mathematics program in the undergraduate level, where the emphasis is on computation and the application of computation. So this is the direction that this university is taking to align itself with present and future. Now, the other signature part of this university, of the leadership, is how we deal with this unusual, unprecedented situation of the corona lockdown. And there was an unambiguous directive that we need to care about our students. There are 150,000 students who are under our care, and we need to encourage and engage the students. And this method or this medium of webinar, using it to getting them engaged and encouraged, that is one of the medium that we, and here I must thank all the institutes we have partnered with. We have done the School of Natural and Applied Sciences has done several webinars in association with institutes like National Institute for Foundry and Forge Technology, NIT Durgapur, SRM University, and today we are very fortunate, and we are really we are enjoying to do this webinar in association with IISER Kolkata. Now, one of the, you must have noted, or it is my duty to point out, that none of our webinars there is any registration fee. because we want to keep it accessible not only to our students, but also to students and participants across the board at large. And I extend, on behalf of the university, I extend my heartfelt gratitude to all the keynote speakers and all the panelists who have donated their time, their extremely busy time, so that we could extend these sort of events to the benefit of the students without charging for any registration fee. So with that, I would get to my brief presentation. And again, let me point out that after someone like Professor Saurabh Pal, this is quite a big shoe to fill, and I am not going to attempt to fill, but I would like to say whatever little I know and I feel in the field of which is relevant to the topic of today's seminar. About a few years ago, the Royal Academy of Engineering ran a survey asking people, not just lay people, but lay people, students, professors, scientists, what are the 7 engineering wonders that make life better in the 21st century? And the answers came like this. Of course, we could guess YouTube and iPhone. However, there were examples, Gore-Tex, which is a special kind of textile, that made the list. Dolby Atmos, which is a sophisticated audio environment, which we have gotten used to gradually without realizing. Hawkeye, a ball tracking system that has made sports, that has transformed sport. 3D printed bone implant. And something very close to my heart is clean water. And this is science and engineering as well. Now, what is there common there? Is there any common denominator here that we can see? What I find is all these solutions, as Professor Paul pointed out, it is not just physics, chemistry, but these are solutions. They involve mathematics, design, manufacturing, modeling and simulation, physics, chemistry, and environment, energy, ecology, artificial intelligence, natural intelligence, biomedical engineering, optics, cognitive science, machine learning, you name it, bacteriology, rheology, psychology, haptics, waste management, economics and business, policy, and geopolitics. However, these have worked together. People have worked together. Ideas have intermingled together. And the borders have disappeared, and borderless integration of diverse applied knowledge has actually made those solutions become reality. So this is what, in a nutshell, computing or intelligent computing, computational intelligence, whatever term you'd like to use, this is what it does. The focus of science, in a sense, is matter and energy, manipulating them. And the source of intelligence, be it natural or artificial, is information processing and communication. Now, the transformative power of computational tools of learning emerges. It is an emerging property, by the way, emerges from the synergy of integration, inclusion, and interaction of ideas and individuals. These ideas and individuals might be specialists. They are indeed specialists. They are specialized in certain fields. They are domain experts. However, there is intermingling, interaction, inclusion, and integration enabled by computing power. So the way the computing intelligence has evolved from abacus to wearable. that means something special to something rather commonplace. What is common there, what we can see, what are the key things? One is the computing power, and all of us know about this Moore's law. The computing power has increased significantly, exponentially. And it has become accessible, user-friendly. Not just by these fancy devices, but now we have devices, pretty much everyone, which has tremendous amount of computing power. Not only that, we have access to local, regional, national, as well as international computing centers of sorts, and databases and tools, which was not there much before. And that is what actually is fostering this integration and inclusion and interaction. The organizers, especially the coordinator, told me, sir, you have to say a few words. And I prepared up to this. And then when I checked with him, he said, sir, this few is too few. So I had to add a few more. Please bear with me. The transformation of science, education, and research through computer-intensive tools of learning, as sir has pointed out, it is essentially an integrator. There is physics, chemistry, math, biology, art sciences. There are interaction, and at the core, it is the computing, intelligence computing, that is helping in education and research. I will focus mostly on the education part. It is time that we asked the forbidden question in education. What has primacy, learning or teaching? What is of central importance? This is a controversial issue. Being a teacher, I know, but unless I ask this question with ruthless honesty, I cannot improve myself. My community cannot improve itself. So I and many of us take the position that teaching serves learning. So that is the perspective that from which I am going to proceed further. Now, here, I'm going to get into online certain aspects of using computer intelligent tools. However, there is some caution in order, and I need to point out that just going to the internet, going to the YouTube, enrolling into certain courses, there are so many of them, and post-COVID, there have been mushrooming of online learning materials. I am not talking about those. I will not. So please, what I'm going to bear with me, because this is very important that I clarify. Most of those tend to make learning or education convenient. Make no mistake, learning, especially science learning and education, is not easy. Convenience actually comes in the way of true learning. Learning anytime, any place sounds pretty attractive. However, actually learning is difficult. The idea, based on serious research and popularized by Malcolm Gladwell, that becoming an expert in any subject takes at least 10,000 hours of practice, of learning, deliberate learning. Science learning takes deep work. And by deep work, I mean cognitively demanding work, where we work on a single topic for a long time with complete concentration and without distraction. So that is required, and just going online is not going to help. It's like reading a newspaper, not on a paper newsprint, but on your screen, and thinking, I am becoming technologically savvy. I'm using online, I'm going digital. That doesn't really help. However, because it doesn't really help, but there is a story, it actually sometimes it's come in the way. There is a story that goes after Michelangelo, who is one of the legendary sculptor and artists of all time. Apparently, the Pope asked Michelangelo about his perfect sculpture, the David. How did you make the David? And Michelangelo's answer was via negativa. That is, I got a big marble block, and from that big marble block, I removed everything that was not David. So there are blocks in learning. Learning being difficult, science being difficult, there we might get misled. We might be moving around the same place, going round and round. So the computers or the computing ability, the two things that I pointed out, the computing power and the user friendliness, it might help us remove these blocks. And that is how there is a paradigm change, and I'm going to talk about the paradigm change. And what I just cautioned you about, cautioned us about, and there is some evidence here because this is from the New York Times, 8th of July, a report that shows the college courses online are disappointing. More than 75% of the respondents said that they were not satisfied. And it was not just from any Tom, Dick, Harry university. Courses given online by Cornell University and UC Berkeley, they were not satisfactory. So going just instead of taking your classroom, a large classroom, just using some fancy gadgets and projecting to another screen is not. As Sir pointed out, that explanation, connecting, and inspiring is required. And I would like to address them, or indirectly, how. So this is my framework, how it could be done in a fundamental fashion. How transformation of education could be driven by computational intelligence in a fundamental way, not just changing things from classroom to the cloud, not just going from paper to an LED screen. First, in this changing paradigm shift is changing the learning style. I mean, how from exogenous, teacher-centric to and imparted knowledge. So typically what happens is the way we learn is whatever the teacher says, and we accept that, and the knowledge is imparted. We actually use these terms, imparted. In many of the papers, if you do, you will find for education that there is knowledge is imparted. The change is required from exogenous to endogenous. That is autonomous, learning-centric, the learner-centric, where the learner is going to discover the knowledge himself or herself. And the guiding philosophy could be found in the word education, which comes from the Latin educere, which means to draw out. However, draw out from the individual. However, what I find more inspiring is The saying by Vivekananda is education is the manifestation of perfection already in woman. So basically, it is an autonomous approach where knowledge could be discovered by the learner. And we will see if computation and its information and communication technology help us in that direction. And the exemplar that I'm going to use is self-organizing educational environment or learning environment or the soul. Then comes the next dimension, which is passive, that is learning by following. Just noting down whatever is being written on the blackboard or fashionably now on the whiteboard. So seeing and hearing and basically learning from that. And what the damage it does is atachophobia. Atachophobia means basically fear of failure, fear of error. However, we are asking people to be innovative. We are asking people to be entrepreneurs. We are asking people to be the Indian Bharat, to be Atmanirbhar. Now, if the youth of India is learning in a passive fashion, in a Paranirbhar way, how can India or Bharat become Atmanirbhar? So there ought to be a change in the paradigm from passive to active learning by doing. And when you do learn by doing, there is a spirit of exploration. There is trial and error. People are not scared of making errors. By going through this iterative process, one can become a better learner. And there is an anonymous saying which goes, I hear, I forget. I say, I remember, I do, I understand. And I think that is the guiding philosophy of this paradigm. And I would demonstrate it to you using some interactive simulation called PHET, which is hosted by the University of Colorado. The third dimension is this from discursive to dialectic. The discursive learning or education, it is expected that the student would accept in an unquestioned, unqualified fashion whatever is said by the teacher. However, as Socrates has pointed out, an unexamined life is not worth living. Basically, knowledge is going to be productive, fruitful, fructifying if it is dialectic. Dialectic means it has to be critically examined. What if analysis has to be done? An active studying has to be done. An active student asks questions, consider alternatives, and questions assumptions. So that is what is the dialectic approach. And there, the philosophy of that dialectic approach I find, other than Hegel, is what Francis Bacon said, is education is the ability to see similarity in differences and differences in similarities. And I would try to demonstrate some computer-aided system that is available out there called explorable explanation, where the text is not just for there, static. It is not information to consume, but the text and as an environment to think in. So this approach, this is what it could do, this paradigm shift is going to create, it has the potency to provide to the student a laboratory environment where he or she could translate thoughts into actions and experiments in real time. And that is critical. And high quality knowledge with little variability, consistent and fair information delivery and assessment, and immediate feedback. And why do I mention consistent and fair information delivery? Let me share a story with you that I heard in a small group setting from from a very senior person. I don't want to name his name, one of the top founders of one of the big IT companies of India. He mentioned that he and his wife had been urging one of their old domestic help persons to open a bank account. And he refused for decades. And it is, I'm talking about in the early 2000s. And then one day, this individual, let us call him Ram, came to this guy, this CEO, and said, "Sir, I'm going to open a bank account today." And he said, "Why? You have been resisting so long." Then he hesitated, Ram hesitated, and he said, "Can I speak freely?" He said, "Yes, of course." Then Ram answered that, "Sir, now there are ATMs." "What is the big deal about ATM?" Then Ram said, "Sir, when you go to an ATM and I go to an ATM, the ATM treats both of us exactly the same way. But when you go to the bank and I go to the bank, the individuals attending the counters or the fancy air-conditioned rooms, they treat you and me very differently. So this consistent and fair information delivery and assessment is something that is very, very important. All of us have experienced it. All of us need to be vigilant about it, that we don't do it. However, these computer-aided systems could do it. So what this is going to do, the idea is basically to make us free thinkers, to make us inventors, make us innovators, so that we could eventually contribute to the development of the society, to the progress of humanity. So science is that which liberates. Sa vidya ja vimuktaye. And how are we going to be liberated? How is education going to be liberated from the quadrant of passive, exogenous, discursive education to the liberated, dialectic, endogenous, active education? And intelligent computing and computer-aided approaches come to help. And they provide quality, access, equity, and of course, individuality. They respect the individuality of the learner, because there is a big difference, sir pointed out, about the importance of history of science. Now, the history of science education, what it points out, it is essentially education, and science education was limited to only a handful, few people in the world traditionally. 10 years ago, 20 years ago, 100 years ago, 500 years ago. However, now education and science education is a mass process. And we have to have this equity, access, quality, as well as respect for the individuality, because otherwise we are not going to be successful. The first one, that is about the exogenous, the autonomous learning. It is the very famous experiment called the hole in the wall by Sugata Mitra. He was then in Delhi, and there was a wall separating, typically a proverbial wall, actually physically there, from the affluent side of the city to the underprivileged side of the city. And he basically, there were a lot of slum dwellers and the kids, and he put a hole and put a computer. The purpose was connected with the internet. The purpose was simple, to find whether students or individuals can learn on their own, unaided by any teacher. So there were experiments carried out from 1999 to 2013, that groups of children, typically 8 to 13 years old, and the results were heartwarming, that can learn to use computers and the internet by themselves, irrespective of their demography. Doesn't matter whether they're a boy or a girl, or Hindu or Muslim or Sikh or Christian, or rich or poor. It was also found that they can achieve educational objectives by themselves. They could complete standard school examination in mathematics and computer science, and also improve English pronunciation without any teacher. This is self-guided learning by groups of children. This is autonomous learning. And it showed that self-organizing behavior resulting in learning in minimally invasive environments and understand the content also ahead of their time, in the sense, for example, if they are equivalent to class 7, they could understand content equivalent to class 8. Now, this hole in the wall has now transformed into a project called School in the Cloud, and there you see there are so many places it is present now. So there are these these links there, if any of you are interested could go, and these are some of the results that shows the pre-test and the post-test, that in, for example, molecule chemistry, the improvement was this significant. In radiation related questions, so basically mean scores in GCSE, that's in England, that is a standard test. So what is the importance, how this sort of learning could, this sort of an experiment, this can actually translate into effective learning. So this gets us to the very first one, where from exogenous to endogenous, this is possible. The computers can help people to become autonomous learners. So point number one, the paradigm point number one is now established. Point number two is about going from passive to active. I would show you an example of what is called PhD, interactive simulation, and this was founded in 2002 by Nobel laureate Carl Wyman, and it became a vision to improve the way science is taught. So this is hosted in the University of Colorado, and this is open access. This is what I'm trying to point out, that just because I do not belong to a country, I do not belong to an establishment which is affluent, does not mean that I or my children or the children of people who work in my household cannot have access to top-notch or really modern facilities, learning environments. So this is free, and I will just demonstrate it in a minute. The other one is called explorable explanations. This is again where we would see that going from the discursive to the dialectic, asking questions, questioning assumptions, and testing scenarios. So bear with me for a second. Let me change the screen. Okay.
Sir, we are missing your screen, sir.
Okay, first I'm going to the explorable examples. So this is a text. And the premise, typically text, we know is static. It gives us information to consume. It does not enable us to do experiment, to think, but this is the idea of Brett Victor. And here, this actually shows a digital, it's a filter, it's a circuit design. Those of you who are expert would know, for example, if Professor Sinha is there, would know it. What I'm going to show is here, in a textual environment, you can do interaction. I can move, I can change the situation. You see, as I am moving, the variables are changing. I am exploring different scenarios. The student is exploring different scenarios, and sometimes the scenarios are infeasible. It is unstable, so it is shown as red. These are actual real data, real interaction is happening. and just imagine the students and the teachers together, or how the how learning can, or education can come to life. The text, this is the potency, this is the fundamental, this is the potency that information technology, computing power has, not just giving us, making us reading on a screen. However, we do not use this. It is not yet mature, it is not yet practiced. This is also, again, this is free. And it gives me happiness to point out that in MAKAUT, we are trying to use some of these truly transformative computational tools for education. Let me go to, just a second. Now I'm coming to what I call PHET. This is basically a laboratory environment. This is about diffusion, gaseous diffusion. So number of particles, you want to introduce how many? Let us, this blue, introduce 100. A number of particles of red, let us introduce maybe 50. Mass we would like to change, okay, atomic mass unit. Would you like to make the red heavier? Let us make red heavier. Radius the same, initial temperature. Now there is scales is there, stopwatch provision is there. I can have a center of mass, etc. What is not there? There is no instruction. So this is learning by doing. You tinker, you see what is there, these parameters are there, and you play with it. You basically discover what happens when you remove the divider. You can keep the time with the stopwatch. Here you can play it. You can measure how far the atoms are going. And a variety of, let's say I want to do some reset. I want to make the radius of this one larger. Now, no theory is said before. This is how actual the inventors, the scientists we talk about, we revere to, they figured things out. So imagine a young person learning about gaseous diffusion, and there are plenty of other simulations like that without instruction, but discovering the knowledge. So these are the three examples that I try to share with you to basically demonstrate the power of computers truly fundamentally changing education. Namely, it can change from exogenous to endogenous, that is autonomous learners, from passive to active learners, and from discursive to dialectic style of education. Now, let me go to research. There is very little that I am qualified to say after Professor Paul. However, just a fact sheet that how much of computing power has increased and how much of computing is used in science. Actually, this little is for engineering and technology, and most of this of computing is used in science. Now, how the process, this is a conceptual nutshell, the research, how the knowledge is generated or created. Basically, there is data and there is correlation and there is theory. Together, solution, as Professor Paul pointed out, all the knowledge is built. And data comes from experiment, literature, databases. Laws of science gives us the theory which validates what we know. And of course, there is correlation comes from inference engine. And what is, in a very simple way, an inference engine could be a graph that we used to plot by hand before. However, with the advent of computers, these things are changing in volume. So data, for example, with materials is becoming huge. And two things, the hierarchy, that data at different scales, as Professor Paul pointed out, different scales is very important, and also heterogeneity of data. That is, there could be data in terms of, for materials, there could be data, for example, the crystal structure data, there could be microstructure data, there could be processing data, there could be different properties data. So data from a heterogeneous data. Then we have these, basically these different correlations. These are data analytics, there's machine learning, and there's big data. So all the, now with the computer, that is becoming possible, and that is becoming not only possible in the sense, but it is becoming accessible to a large number of people. You really do not have to be the best scientist or the computer scientist of the world or of the country. Being a reasonably median person who can approach this. And there is collaboration, and this is a critical contribution of computing ability, that the collaboration is taking place. And what this is doing is also accelerating the knowledge discovery process. So I would give an example of that shortly. This didn't happen overnight. So the structure of scientific revolution, that there is one paradigm, that is one way of understanding, one way of doing things, gradually comes into some sort of a stone wall. It is not adequate, and then another paradigm kicks in. So early, the very first one was the experimental, empirical science, tinkering, trial and error. Certain people would be Joseph Priestley, Lavoisier, Faraday. Then came the model-based theoretical science, the second paradigm. For example, the laws of thermodynamics. Again, some of the stalwarts here could be such as Schrodinger's, Maxwell, Bose. Then the third paradigm is using computational science. For example, as it has been so well explained, using the density function theory or molecular dynamics. And eventually, currently, we are now on the fourth, that is data-driven science, that is the big data. So predictive analysis, clustering, and the like. So what is happening once this data, big data, data-driven science, here we have, these are certain features. The model, it gives a conceptual model of it, and the Materials Genome Initiative has kicked in, and there we have experimental tools, digital data, and computational tools, which is validated by theory and the physics in the context of human welfare, sustainable environment, and renewable energy. So that is where gradually, how there is the evolution from paradigm to paradigm, incorporating computational intelligence computing or computational intelligence, whichever way you would like to phrase it, incorporating that in the wings, under the wings. So this is the conceptual architecture of material science research in the age of computational intelligence. Now, why material science? Because a large number of chemistry and physics actually concerns materials, and also there's a bias. I come from that background. So here you see that there are theoretical databases, then libraries and imaging libraries, and there is integration is taking place. This is this interaction and integration. That is where the computing and the computing powers comes in picture. However, it is important that I caution myself here that pretty pictures like this are misleading, in the sense that it gives you a bird's eye view, a view of the landscape from way above. But the devil is in the details. Actual doing takes a lot of work, and you got plenty of examples of that from Professor Paul's presentation. So this is just giving an idea how things are connected. Now here, there are large number of databases and tools that are available open access now. For example, OQMD and the materials database and materials project and the like. So these are all readily available and open access. And here, this is the central dogma of material science research. This is the human needs and desires, that's the performance, then the properties, then the structure. And the structure as hierarchy and heterogeneity, like those Russian dolls. What is crucial to note here, that the processing or composition in this direction, it is many to one function. So the science and the researcher, the cause and effect goes this way, but the materials discovery takes place this way, and there is a lot of uncertainty involved. These are the inverse models, and these are the forward models. This does the prediction, and this does the discovery. So basically, this is the schematic pathway of prediction and discovery in material science. We have already talked about it. Let me skip over it and end with an example. When we say carbon dioxide, the word is bad reputation. In most of us, and mostly in the environmental lists. However, scientists at the Joint Center for Artificial Photosynthesis view CO2 as a promising solution to clean, low-cost renewable energy, using a process called artificial photosynthesis, which harvests solar energy and stores it in chemical bonds. If successful, they will be able to produce fuels while also eliminating some CO2, a win-win situation. New efficient photocathodes are a major hurdle to realizing scalable artificial photosynthesis. Why? The existing photocathodes have very low efficiencies and product selectivity. Now, previous experimental attempts to find new photocatalytic materials by trial and error were rather slow and unreliable. So, using supercomputing resources at the National Energy Research Scientific Computing Center, the Berkeley lab team performed a massive photocathode search, starting with 68,860 materials and screening all of them for specific intrinsic properties. The candidate materials needed to be thermodynamically stable so they can be synthesized in the lab. They need to absorb visible light, and they need to be stable in water under the highly reducing conditions of CO2 reduction. All these three key properties were already available through the materials project database. So here the solution came using, again, computing power and the 6-step selection criteria: PB, the thermodynamic stability, PB band gap, aqueous stability, small lattice, H, and all the gaps. From 68,860 possible candidates, 52 eventually were funneled down, and then they were walked in laboratories, and solutions were found in about 2 years. So that's a remarkable acceleration of materials discovery. A lot of examples have been given. Examples are plentiful, but understanding is rare and insights rarer. I didn't go into, there is not much of time, nor am I an expert in giving you a lot of examples. However, in my search for insight, I ran into 3 4-letter words: atom, for manipulating matter and energy, byte for manipulating information and communication, and gene for manipulating life and life forms. All these three relate to science. These four-letter words and the power inherent in them are shaping science and civilization today. These are the trident of transformation. Thank you for listening.
Hello. Tapas? Hello.
Thank you, sir. Tapas sir, are you there?
Tapas sir, are you there?
Hello, Tapas sir. Tapas sir, kindly unmute your mic.
Yep. Can you hear me now?
Yes, sir. Yes, sir. Yes.
Yeah. Okay. So thank you, sir, for sharing your thoughts and such necessary information and aspects of computation in such a lucid manner. And I hope the attendees definitely have so much to follow and explore the concepts that you discussed in depth in such short span of time. So they have ample time to explore that all the parts and all the new examples to them, I guess, in near future, and imply them in their own expertise or in the field of their domain. And now may I request Dr. Bagh and to move into the discussion and the question answer sessions. So Professor Pal can answer them. I think
yeah,
sir already have answered in the chat box.
Yeah, I mean, most of the people who asked the question, they have left now. I think you should have finished the question answer right after my talk. I don't know why
Sir.
such a long gap. Many people have left. I have tried to answer, so I don't know. I mean, if somebody is there, I've answered.
Sir, we have few questions. I should ask Dr. Bagh to please go through the questions and so that sir can answer them.
So that's what I'm saying. I answered many questions in the chat.
This question has been answered.
Yeah, sir, we've seen that you have already typed many answers.
Asked the questions have already left.
Okay.
So
Okay,
I think we should have finished the question answer immediately after my talk. That is what I feel. Because there's a long gap. You understand what I'm saying? Yeah, anyway. So if there is any question, I think I have given answers to most of the questions. Somebody wrote that marks are a problem. Somebody asked when is the next webinar. Somebody asked how do you relate computer science with a science like chemistry. So I wrote all the answers actually. That computer science can be used as a tool in scientific research, chemistry research. So I don't know. Then somebody asked how computational chemistry is a new trend than doing theoretical chemistry. So I wrote what is the difference between computation and theory. That computation is basically applying theory to chemical problems. And the new trends probably will emerge from new theoretical algorithm developments and data science development, like artificial intelligence, machine learning. So that could be a new trend in the computational chemistry. Somebody asked, what is for an experimental chemist at his or her middle of career, what is the main challenge in adopting aspects of computational chemistry? How to deal with that issue? So I actually answered that it is not very difficult. Today, learning computational chemistry, even middle of the career, is not that difficult. It is indeed possible. Then let me see what are the other questions. Questions from GP Das. I don't know if GP Das is here or he has left. Because his questions are more technical. So I told that, yeah, he's there. So yeah, thank you, Professor Das, because he has asked more technical questions than others, because he is in the area computational science. So let me see what he has asked. He has asked that with the advent of data science, is conventional experimental science, in particular laboratory chemistry, slowly redundant? How can one extrapolate things to come in years to come? So I don't think Professor Das, I mean, of course, I know him very well. I can call him Gaur, but I don't think this will happen. That the conventional experimental science, laboratory chemistry will become redundant because of data science. Because there is something to do with your own hands, experiment. I think that will never vanish. That is my question. Even I don't see in years to come. I don't know what will happen in very long time, but not in immediate things. The second thing is that he has written ab initio MD, which has so far been restricted to only 100 atoms, is now conjectured to be carried out to million atoms by a generation of the force field via the so-called deep potential molecular dynamics. See, I have heard about it. I mean, it is possible that the force field is generated very, very fast. So basically, the force field generates very fast, and one can actually go to much larger system, much larger number of atoms. So yes, I have also heard about it, though I have never used this deep potential molecular dynamics. His third question is, what is the current status of the so-called periodic coupled cluster theory in computational material science in the numerical framework of numerical atom-centered orbitals and the projector augmented method? Okay, I am aware that there are groups who are working on periodic coupled cluster theory. I don't know if they have worked in the atom-centered orbitals, but initially they were using periodic basis. Okay, obviously projected augmented method can be used. That's not a problem. But if they use atom-centered orbitals, then obviously this will be very difficult to use for material science. So I think for material science, one has to use a periodic basis, but PAW, projected augmented wave method, can be used in conjunction with that. So these are my answer to his questions. I think he's still there. So then let me see what is the other question I have not answered. Could you please suggest one or two textbooks? I actually wrote, Christopher Kramer, Essentials of Computational Chemistry. There is another book by Computational Methods and Simulation. But there's a whole lot of books. You can go to Google and find Essentials of Computational Chemistry by Springer. The Springer publication by Christopher Kramer. He's very famous. I think it's a good book. It covers a lot of things. It's 2004 paperback edition is available. Okay. And mathematics, the required mathematics is there in that book, and also in a textbook called by Modern Quantum Chemistry or Advanced Quantum Chemistry by Szabo and Asloon. All right. The next question is, online teaching will be equally as like offline teaching that we had before COVID. Will you prefer complete online teaching, as many universities are shifting for that direction? Okay, what he's asking is that in the COVID era, subjects like physics and chemistry, which have experiments, will you prefer complete online teaching? I don't think, I would say I prefer online teaching. Today, online teaching is a necessity, but I would not say it's a preferable thing, because I still believe classroom teaching is much more effective than the online teaching, both for theory classes and experimental. So that when I talked of online teaching, I think we have to understand that I was merely talking about online teaching in the context that it has become essential. However, online teaching has certain advantages. I said that anybody can join anytime from anywhere. So that's a big advantage. So somebody like you are teaching, somebody can join from US, Europe. I in fact joining a lot of webinars which are going on from Europe. Just recently I joined a webinar on VASP. So I think that's a big advantage in online teaching, that you can join from anywhere. However, so online teaching is also very important. Good. I think there has to be a mixture. It is not online versus offline. After COVID era, I'm pretty sure both will stay. Both will stay. So I think it is very important that we should understand that online teaching is also going to be important, as well as offline teaching is necessary. Because If offline teaching completely goes off, you cannot, not only even in theory classes, you cannot explain properly, but also the laboratory experiments cannot be done. At the same time, with online teaching, you can reach many more people. So I think there are certain subjects where online teaching may not be so difficult. So I think we have to do a mix and match. That is and that is what is going to happen eventually. So this is by Anindo Sundar Manna. Then there is somebody who is anonymous attendee has written, why we don't talk about our ancient Vedic science. Now I did talk, I actually answered, I did talk, ancient science was well developed. We have lost some of the things links, and I think we have to bring back. So I'm certainly saying I am not biased for or against. And next was, let me see, next is again 1 or 2 textbooks, which I've already written. Then Dr. Indranil Kundu, he has also written, can you provide some e-books related to computational chemistry? I already answered. Essentials of computational chemistry. I think that's about it. Yes, GP Das has written that yes, he's in the meeting. I answered your questions, Professor Das. And if there are more questions, we can discuss offline. All right, so I think that's about it. Let us see. Yes, so Professor Das has further replied that as far as the last question is concerned on periodic coupled cluster, he wants to comment that the practitioners of periodic coupled cluster are trying to establish a relationship with random phase approximation originally proposed by Bohm and Pines. Right, that is true. In fact, I would say very recently in the periodic system like VASP, there was a lecture by Professor Martin from University of Vienna where he showed that how to go beyond DFT. And he actually showed that by taking something from the random phase approximation, one can actually go beyond DFT. So I think DFT he showed is good, but in many cases for catalysis and all that, transition states or barriers are not coming correctly. So there is still an improvement one has to do. And they actually showed random phase approximation as a way to improve because it has some link with the coupled cluster kind of method. Again, it is a little technical to answer, but yes, my answer is yes, that many people are trying to establish this relation. Okay, I think more or less that's it. Aravinda Chaudhary, he has written, great talk. Do you think CGMD calculations can predict relative fusogenesis of nanometric drug delivery system? Yes. The answer in short is yes, but I think the models of these membranes have to be done properly because I don't think even in coarse-grained molecular dynamic simulation, that's what he means, CGMD simulations, we'll be able to do a complete membrane calculation yet. But I think there are reasonably large models of membrane for which coarse-grained molecular dynamics can be done. But people are doing it. There is a software called GROMACS. I can refer him. GROMACS, which is from Groningen, Netherlands, which has coarse-grained molecular dynamics simulation. You have to probably check how large a system it can handle. It is possible, I think. But at least if it is not possible, it will be possible very soon. Because these are all parallel programming. So you have to understand, depending on the number of nodes, number of computers that you have, you can scale up this calculation. So in short, Professor Aravinda Chaudhary, in short, the answer is yes. I'm typing out the answer to him privately. Yes. So I think more or less that's about it.
Sir, I have a question from my end, sir.
Yeah.
If you have answered all of them, sir.
Yeah, I think so.
Yeah. So it's a question from the point of view from a synthetic organic chemist, because I am so, and I work on the synthesis of organic photovoltaic materials containing fullerenes. So what would be the best practice for a person like me to adopt when we are talking about incorporating computational approaches into the research? So is it collaboration?
Yeah, for synthetic organic chemistry, there are two things that are required. One is, of course, to know the thermodynamics. So reactant and product, that is very easy to measure. So today we can measure enthalpy as well as entropy and get a free energy of reaction.
Yeah.
But what is important for synthetic organic chemistry is to understand whether the synthesis will go or not, to get a complete reaction profile from reactant to product, get a reaction mechanism, because it will go through some transition state, it will go through some intermediate. So to get a complete profile, then if the barriers are not very high, that means you know that the reaction will go through.
Yeah. Feasible.
Feasible. So typical barriers, which should be about 20 to 30 kilocalorie per mole, I think, which is okay. Okay, but if it is very high, then by the Arrhenius calculation, you can immediately see temperature will go up. If something goes off at room temperature at the 20, let's say the 20 energy value, it becomes 40, temperature has to be double in Kelvin, not centigrade.
Okay.
So that is a huge difference. So 300 degrees Kelvin becomes 600 degree Kelvin.
Kelvin. Yeah.
That is very simple Arrhenius equation. So then your reaction will not be feasible. So your synthesis cannot be done. So that is why computational chemistry can play an important role in synthesis. So basically, you need to know how to calculate transition states. So hence activation barrier in a complete reaction profile as a reaction goes to product. And of course, initially get the thermodynamics, both delta H as well as delta G. And those can now be done at various levels. So depending on your system, you can even do couple cluster, but that is very expensive. But you can certainly do density functional theory, DFT. That is what people are doing. Although I told you the dangers of DFT, the DFT is not always very reliable, but I think it is still doable with the DFT.
Yeah. Thank you, sir. Thank you.
Thank you, sir.
So, thank you, sir, for your generosity to answer the question in the chat box and as well in the question answer session. And may I now request our head of the department, Dr. Atri Bishwas, to give the formal vote of thanks. And then we will conclude the sessions. And before I move to Dr. Bishwas, I would like to say to the participants that the links for feedback form and certificates have been provided in the chat box, so you can have the link. And after 2 hours or around so, you will get the certificates once you form the feedback form. So over to Dr. Bishwas for addressing the formal vote of thanks, please.
There is one more question that has now come.
Oh, sir, please, sir. Feel free to answer, sir.
Paul Majumdar.
Yeah.
What is your idea on imparting such abstract moral values and ethics that has been a part and parcel of our fundamental beliefs of our country, while we switch how to do online teaching? Which one? Won't you get more machine and lose the basic instruct being a human? And then environment would get more disturbed when one imbibes only technical and self-centered knowledge since childhood, from Shantiniketan to online mode. I think she's asking, if we go to online teaching, are we going to lose some ethics and moral values because people will only be hooked to the computers? I think it's a concern, no doubt. That is why I said that you should not forget that we have to teach. Even if you online computer tools and all that, finally that teaching is inspiration, teaching is imparting moral values. So that has to be done in some form. So yeah, I mean, it can happen if you have only online teaching for a very long time. But my answer to the question is that that is probably not going to happen, hopefully. It is a necessity in the short run. Okay.
Thank you, sir. Thank you. So may I now request Dr. Bishwas to please address the vote of thanks.
Hello, Atri Bishwas, ma'am. Hello. Hello, ma'am. Are you able to hear us?
Yeah. Sorry, I muted my speaker. Am I audible now?
Yeah.
Yeah. Honorable Vice Chancellor, our Director of School of Natural and Applied Science, our most valued invited speaker, the coordinator, my colleagues, and all the respected participants. It's an honor for me to deliver a vote of thanks on this occasion. I, on behalf of Applied Science Department, first of all, express my sincere gratitude to our Honorable Vice Chancellor, Professor Shoikat Moitro, for providing us encouragement and continuous support to organizing this event. I believe we will continue to get his generous support in future also. I extend a very hearty thanks to our Director of School of Natural and Applied Science, Professor Sukhendu Samajdar, for his active participation and guidance right from the beginning. I heartily
Hello.
I express my sincere thanks to our honorable delegate, today's keynote speaker, Professor Saurabh Pal, who blessed us with his presence and took out valuable time of his busy schedule. We had a very insightful information and knowledge from his discussion about the prospect and role of computation in the context of education and research in various scientific fields in future. My special thanks goes to Dr. Taposh Ghosh, who is the coordinator and key person in organizing today's webinar. I sincerely thank him for giving us opportunity to organize such an event from our department. I would also like to extend my sincere thanks to Dr. Orijit Bang, who played a significant role in the conduction of today's event. I heartily congratulate all the participants who registered and actively participated in this almost 3 hours long event. I see some of the distinguished personalities joining our webinars like Professor A.K. Tiwari, Professor Debashish Kole, Professor Poshun Mondol, Professor Alokesh Bisai from IITs Kolkata, and many other faculties and students from different colleges or universities across the country. Thank you very much for giving your precious time in this event. Finally, as no program can become successful with a single person, I extended my big thanks to our faculties of Applied Science Department as well as our technical staff, Mr. Prem Kumar and Miss Kwelde for their constant support. Thank all of you for making this event successful with your contribution. Now, with permission from all, I conclude this session here. Thank you for your time and wish you all a safe, healthy, and great time ahead. Thank you very much.